this section, you will learn about the integration of inverse trig functions. First up, we need a little algebra review on completing the square. Suppose you had this expression 3x squared minus 24x plus 35, and you wanted to write it using completing the square. The first step is to factor the 3 out of the x terms. So we would write this as 3 times the quantity x squared minus 8x. Now I'm purposely going to leave a little bit of space here because we want to complete the square, and then I'm going to take the plus 35 and throw it on the end. To complete the square, take half of 8 and then square that number. Half of 8 is 4. 4 squared is 16. So inside here, I wish I had a plus 16, but we can't add in a term without counteracting it, otherwise we've changed the expression. Now you have to be careful to remember that you're not really adding in 16. What you've really added in is 3 times 16, which is 48. So then to counteract that, you have to subtract 48 on the outside. Now what we've really done is added 0. We've added 48 minus 48. And then to write this in factored form, we would get 3 times the quantity x minus 4 squared minus 13. So pause the video and try this one on your own where you complete the square on this expression. Then restart when you're ready to check your answer. Here we would factor out a 2 from the x terms and have x squared minus 5x, leave a little space, and put the plus 1. We need to take half of 5 and then square it. So that's going to be 5 halves squared, which is 25 over 4. So on the inside, I will add 25 over 4. But remember, it's not really 25 over 4 that I added. It's really 2 times 25 over 4, which would be 25 over 2. So to counteract that, I have to subtract 25 over 2. So now, when I simplify this and write it in factored form, I would get 2 times the quantity x minus 5 halves squared minus 23 over 2. Because 2 over 2 minus 25 over 2 is negative 23 over 2. Here are the formulas for the integrals of inverse trig functions. Let u equal g of x and du equals g prime of x dx, and let a be a constant such that a is greater than 0, then we will use these three formulas. The integral of du over the square root of a squared minus u squared is equal to arcsine of u over a plus c. The integral of du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. And finally, the integral of du over u times the square root of u squared minus a squared is equal to 1 over a arcsecant of the absolute value of u over a plus c. Now notice that we don't have formulas for arc cosine, arc cotangent, and arc cosecant because those derivatives, if we work our way backwards, just would have a negative sign in front of them. Since we could just factor that negative sign out front, then we could turn it back into these formulas, so we don't bother with formulas for arc cosine, arc cotangent, and arc cosecant. You just have to know these three. In this example, we have to integrate 3x squared over the quantity 4 plus x to the 6th dx. Referring to the integrals of inverse trig functions, we see that this integral looks the most like the formula for arctangent because there's no square root in the denominator. So we expect that we will be trying to set up our integral into the form of du over the quantity a squared plus u squared. And that will result in 1 over a arctangent of u over a plus c. So coming back to the integral here, in the denominator we need a squared plus u squared. So if we let u squared equal x to the 6th, then that would mean that u is equal to x to the 3rd. Then du would equal 3x squared dx. And that looks like good news because we see in the numerator we have 3x squared dx, so we already have our du. Now we will also need to let a squared equal 4, which means a is equal to 2. So if we put this all together, we have the integral of 3x squared dx over 2 squared plus x cubed squared. And now we can do our u/du substitution and get the integral of du in the numerator and a squared plus u squared in the denominator. Now that we have this form in our integral, we can apply this formula. So we get 1 over a times the arctangent of the quantity u over a plus c. And now we can substitute back to the original variables, and we get 1 over 2 arctangent of x cubed over 2 plus c. In this example, we have to integrate 1 over the quantity x times the square root of quantity x to the 4th minus 9 dx. Referring to our integration formulas, we can see that this looks the most like the integration formula for arcsecant, and the reason being is that the variable comes first. Notice with arcsine, underneath the radical, the constant term, a squared, comes first, whereas with the arcsecant, the variable comes first, and the order matters because it's a subtraction. If this was an addition, like in arctangent, the order wouldn't matter. But because it's a subtraction, the order matters. And with the variable being first, that pushes us towards arcsecant. So we suspect we will be setting it up to look like the integral of du over u square root of u squared minus a squared, which will result in 1 over a arcsecant of the absolute value of u over a plus c. So let's look under this radical first. We need u squared minus a squared in the format. So let's let u squared equal x to the fourth. Then u will equal x squared, and du will equal 2x dx. We will let a squared equal 9, then a is equal to 3. Now, looking at our integral, we see that for du, we are going to need a 2x dx, and all we have in the numerator is just dx. So what we can do is multiply inside the integral by 1 in the form of 2x over 2x. And now this is going to equal the integral of 2x dx over, we've got a 2, then we have an x times an x gives us x squared, and then we have a square root of x to the fourth minus 9. Or we could have written that as x squared squared minus 3 squared. Now here, let's start to do our substitutions. This numerator, 2x dx, we see can be replaced by du. Now in the denominator, we have x squared, which could go here and be replaced with u. We have the square root of x to the fourth minus 9, and we see that that can be replaced with u squared minus a squared. Then we have one thing left here, which is this constant of 2. Now, because it's a constant, we are allowed to take that out in front of the integral. So that becomes a 1/2. So now everything from the original integral is accounted for in the u variable integral. So we bring down that 1/2 because that's just a constant sitting out there in front. And now let's apply the integration formula on this integral, and we would get 1 over a times the arcsecant of the absolute value of u over a plus c. Now we know we'll be substituting back where a is going to be replaced with 3 everywhere that it appears, and u is going to be replaced with x squared. So we would have 1 over 6 in the front, because 2 times 3 is 6. Arcsecant of the absolute value of x squared over 3 plus a constant. And now we have one more simplification we need to do, because the absolute value of x squared can be simplified because x squared is greater than or equal to 0 for all x, and that allows us to drop the absolute value. So now this becomes 1/6 arcsecant of the quantity x squared over 3 plus c. In this example, we have the integral of dx over the quantity 2x squared minus 8x plus 10. Right away, I see I could factor a 2 out of each of the terms in the denominator. So I would want to rewrite this as 1/2 times the integral of dx over the quantity x squared minus 4x plus 5. Now looking at my integration formulas, I would suspect that I'm going after the formula for arctangent because there's no square root in the denominator. So we figure we're going to be setting it up to look like the integral of du over the square root of a squared plus u squared, which results in 1 over a arctan of u over a plus c. Now we realize to get it into this formula, we are going to need to complete the square in the denominator. Now in order to complete the square, we need to do 1/2 of 4 and square that number. So half of 4 is 2, 2 squared is 4. So then what we have is 1/2 times the integral of dx over x squared minus 4x. I'm going to leave that little space, put the plus 5. And then because of my completing the square process, I realize I need to add 4 on the inside here and then counteract it with subtracting 4 on the outside. Or you could look at it as splitting up this 5 into a 4 on the inside and a 1 on the outside. So now we have 1/2 times the integral of dx over this quantity becomes x minus 2 squared, and this simplifies to be plus 1. Now you also know that 1 is the same as 1 squared. So you can think of this as 1, or you can think of it as 1 squared. It's the same thing. So let's start setting up our u du substitutions. In the denominator, we need a squared plus u squared, which would be the same as u squared plus a squared. So the order doesn't matter because it's addition. So let's let u squared equal the quantity x minus 2 squared. Then that means u will equal x minus 2, and du will equal dx. Then that means a squared has to equal 1 squared, which means a is equal to 1. So this is going to equal 1/2 times the integral. In the numerator, we know that dx is equal to du. In the denominator, we know that the quantity x minus 2 squared gets replaced with u squared, and the plus 1 squared is going to be replaced with plus a squared. Now that we have the integral formatted, we can apply the integration formula. Let's bring down this 1/2 out front, and we have to take that times 1 over a arctangent of the quantity u over a plus c. Substituting back to the original variables, we have 1/2 times 1 over 1 arctan of the quantity x minus 2 over 1 plus c. And finally, this will simplify to be 1/2 arctangent of the quantity x minus 2 plus c. In this example, we have the integral of 3 over the quantity 2 radical x times quantity 1 plus x dx. Now, at first, this integral might not look like it fits in with any of the integration formulas that we have. But one thing to notice is that every integration form has in the denominator a u squared and an a squared. Now, the u squared will always be whichever term has the highest exponent. So in this case, let's try letting u squared equal x, because x is x to the 1, and that exponent is higher than x to the half. Then u would equal radical x, which is x to the 1/2, du would then be 1/2 x to the negative 1/2 dx, which means that du is dx over 2 radical x. Now we will come back in a minute and figure out a squared and a. Let's see what we can do with this integral. Now notice that our du requires that we have a dx over 2 radical x, and we do have a dx available and a 2 radical x in the denominator. So let's write that together over here. Then that means this 1 plus x is left in the denominator, and we would have a 3 in the numerator, or we could write it as a 1 inside and pull that constant of 3 out front. Now, if we start doing our substitutions, we will bring this 3 directly down, We have the integral symbol, make the fraction bar. Then in this denominator here, we know already that the x is going to get replaced with u squared. And then that points us to let a squared be 1, which means a is 1. So then this 1 right here is the same as 1 squared, which can be replaced with a squared. And then this dx over 2 radical x can be replaced with du. So you could write it as 1 here and put the du here, or you can just write the du here. Same thing. So everything from the original integral has now been switched over to the u variable integral. Now when we look at our integration formulas, we see that we will want to use the formula for arctangent. We've got the integral of du over a squared plus u squared is going to be 1 over a arctangent of u over a plus c. So this is where we're headed. We've got that 3. Now we have to take this integral here, which results in this form. So we have 1 over a arctangent of u over a plus c, which is equal to 3 times 1 over 1 arctangent of, remember that our u variable was radical x. We put that over 1 plus c. So this will simplify to be 3 times the arctangent of radical x plus c. In this example, we have the integral of 2x over the quantity x squared plus 10x plus 29 dx. Now I notice that my denominator has an x squared and my numerator has an x. So if we let u equal x squared plus 10x plus 29, then du would equal 2x plus 10 dx. We have the 2x we need in the numerator. We're just missing that plus 10. So let's see what we can do to get that. This is going to equal the integral. We have the 2x here in the numerator, and we have that x squared plus 10x plus 29 in the denominator. We got the dx over there. And what we can do is add in 10 that we need as long as we subtract 10. So all we've really done here is add 0. Now what we will do is split this integral up into 2 pieces. So this will equal the integral of 2x plus 10 over x squared plus 10x plus 29 dx minus the integral of 10 over x squared plus 10x plus 29. And this minus sign right here is from this minus sign up here in the numerator. Now this first integral, we can do a substitution. We see that 2x plus 10 dx can be replaced by du. And in the denominator, the x squared plus 10x plus 29 can be replaced by u. Then we subtract away 10, I'm just pulling that constant of 10 out front, times the integral of dx over, now here I anticipate that I'm going to need to complete the square. So if we come over on the side, we've got x squared plus 10x plus 29. We know that half of 10 is 5. 5 squared is 25. So we could write this as x squared plus 10x, and then we could split that 29 into plus 25 and plus 4. Then this part would be x plus 5 squared, and then the plus 4 I could write as plus 2 squared. So x squared plus 10x plus 29 can be replaced by the quantity x plus 5 squared plus 2 squared. Coming along here, we know that the integral of du over u is going to be the natural log of the absolute value of u. We will get a plus c, but we are also going to get a plus c from this integral, so we will add the plus c on at the very end. Then we have to subtract 10. And now for this integral, we need to do a substitution. Now we've already used the variable u, so maybe we pick a different variable, v, if we want, and we can let v squared equal the quantity x plus 5 squared, which means v is going to equal x plus 5, which means dv would equal dx. So working on this integral to do the substitutions, this dx up here can get replaced with a dv, and then in the denominator here, we know the x plus 5 quantity squared is going to get replaced with v squared. And then the 2 squared needs to get replaced with a squared. So then that tells us to let a squared equal 4, which means a is equal to 2. So then this 2 squared becomes a squared. Continuing to simplify, natural log of the absolute value of u becomes natural log. We substitute for the u variable its definition of x squared plus 10x plus 29. Let's bring down this minus 10. And then we know that the integral of dv over v squared plus a squared is going to be 1 over a times arctangent of v over a plus c. Remember that the v in this integral is acting like how we've been using u, but u was already defined over here, so we needed to use a different variable in this definition. We need to continue to simplify. So the next decision to make is whether we can drop these absolute value symbols. So we have to look at this expression inside and decide if it's always positive or if it's sometimes positive and sometimes negative. So the deciding factor is whether x squared plus 10x plus 29 ever changes sign or not. Now remember, we completed the square on it earlier, and we got to this expression here where we had quantity x plus 5 squared plus 4. We know this part is always greater than or equal to 0, and then we add 4, which only makes it even bigger. So this is always greater than 0, which means that the original expression, x squared plus 10x plus 29, is greater than 0 for all x. And when that happens, we get to drop the absolute value symbols. So we simplify this first term to become natural log of the quantity x squared plus 10x plus 29. For the second term, we have to substitute back to the original variables. So we have minus 10 times 1 over a is equal to 2. Arctangent of the quantity v, which is x plus 5, over a, which is 2, plus c. And then, of course, this 10 times a half can be simplified, so this becomes equal to natural log of the quantity x squared plus 10x plus 29 minus 5 times the arctangent of x plus 5 over 2 plus c. In this example, we have to integrate the quantity 3x to the third minus 2 over the quantity x squared plus 4 dx. Now, I notice right away that the degree of the numerator is greater than the degree of the denominator. And we learned that when that happens, we have to do polynomial long division. So if we take x squared plus 4 and we divide it into 3x cubed plus 0x squared plus 0x minus 2, then to get to 3x cubed when we have x squared, we will need to multiply times 3x. So 3x times x squared plus 4 is going to give us 3x cubed plus 12x. So that would have to go under the x term here. Then we have to subtract that whole thing. 3x cubed minus 3x cubed goes away. We don't have any x squared term, and we will have a negative 12x, we can bring down that minus 2. Now, because x squared won't go into x, this is actually our remainder. So we know that would be plus a negative 12x minus 2 over x squared plus 4. So that means that we can rewrite the original integral to equal the integral of 3x dx plus the integral of negative 12x minus 2 over x squared plus 4 dx. This rational expression here in the integrand is equivalent to this new expression in the quotient here once we do the division. Now this first integral is very easy to do. We get 3 times x squared over 2. We know that we will have a plus c from here and a plus c from there. We'll deal with the plus c at the end. Now for this second integral, the denominator has an x squared and the numerator has an x. So let's try letting u be that denominator, x squared plus 4. Then du would equal to 2x dx. Now notice the du here, we can't have this minus 2 hanging around. So we need to split this integral into 2 more integrals. So we would have minus the integral of 12x over x squared plus 4 dx, and then minus the integral of 2 over x squared plus 4 dx. Now, looking at this u du substitution here, what we wish we had in the numerator of this rational expression was 2x dx, not 12x dx. So what we can do is take that 12 and turn it into 2 times 6. This is still the 12x that we had, but now it's in a more useful form where we can use this to get the du that we need. So let's bring down this 3x squared over 2. We've got minus 6 times the integral. This numerator now can be du and the denominator can be u. Let's continue to do this integration and finish it up, and then we'll go into the next one. So here we would bring down the 3x squared over 2, and then now we get minus 6 times the natural log of the absolute value of u. Again, we would get a plus c from here, but we know we're going to add that on in the end. And we're going to come back and finish this in just a minute. So this is 3x squared over 2 minus 6 natural log absolute value of x squared plus 4. Now here we have to decide if we are going to simplify the absolute value or not. We know that x squared plus 4 is greater than 0 for all x, and that will let us drop the absolute value. So now we have this is equal to 3x squared over 2 minus 6 natural log of the quantity x squared plus 4. Now we are ready to work on this last integral, and hopefully you can recognize that it's going to be in the form for arctangent because we have that x squared plus 4 in the denominator. We don't need to do a u du substitution here because we just have a simple x squared there. So if we just let a squared equal 4 so that a is equal to 2, we can also bring this constant of 2 out front. So we have minus 2 times the integral. In the numerator, we could put that dx there. In the denominator, we could call it x squared plus a squared. Now using the integration form for arctangent, we get minus 2 times 1 over a arctangent of x over a plus c, which is minus 2 times 1 over 2 arctangent of x over 2 plus c, and then finally this simplifies to be minus arctangent of x over 2 plus c. So now all three of these pieces have been integrated to get our result. In this example, we have to integrate x over the square root of the quantity 5 minus x to the 4th dx. It's time to check your understanding, so pause the video to try this one on your own, then restart when you are ready to check your answer. We recognize that this will be in the form possibly for Arcsine because we have the constant first and we're subtracting the variable. So if we let u squared equal x to the 4th, then u would equal x squared, then du would equal 2x dx. We would have to let a squared equal 5, and then a is equal to the square root of 5. Now we almost have the du that we need. We've got x dx and we need 2x dx. So we just have a little bit of work to do here. We've got that x dx, and we have the square root of 5 minus x to the 4th. And we just need to get in there this 2 and counteract it with a 1/2 out front. Now we can do our substitution. We bring down that constant of 1/2 right out front. Integral. The numerator can be substituted with du, and in the denominator we have the square root of a squared minus u squared. So now Let's bring down that constant of 1/2. And then for the arcsine formula, we see that there's no 1 over a out front. It's the only one that doesn't have the 1 over a. So we will get arcsine of u over a plus a constant. So now we just have to substitute back to the original variables, and we get that it equals 1/2 arcsine of the quantity x squared over radical 5 plus c. And we don't need to rationalize this. We're going to leave our answer in this form.